Hello everyone and welcome back. So we left off on the previous tutorial with this equation, and also I realized I forgot to write the ZL here. So this is the equation that we had previously, and we are trying to convert this equation into a form that encompasses the tanh function. Okay, so what we need to do is to convert this piece here, this piece and this piece, into the tanh function. So if you look here, it has exactly the same form as the tanh function, just the x here is replaced by the minus j beta x here. So what we need to do here is we need to rewrite this as z naught. So this is z naught times zl minus z naught, and now this will be equal to tanh. And now remember that tanh x requires a 2x here. It's not tanh of 2x, it's tanh x, and the x here will be equal to the minus j beta x. So this will be equal to tanh of minus j times beta times x. So now we divide here and we write the second factor, which is z naught minus zl times tanh of minus j beta times x. So that's it. If you look here, the x here is the x here, and the x here is the minus j beta x. So we just substitute this into here and we have the formula already. So remember that this is equal to Zin, which is input impedance at any point x on the transmission line. Now if you look here, we have this minus here. However, there's a nice thing about the tanh function, which is it's an odd function. So tanh of x is equal to minus, let me write it down here. So tanh of minus x is equal to minus tanh x, which is an odd function. If you look on the graph of the tanh x, it starts negative here, goes here, and goes like that. So it's symmetrical, and it's an odd function. So we can remove this minus sign here and cancel it with this minus signs here in front. So let me change color here. Zin will be equal to z naught times zl plus z naught times the tanh of j times beta times x divided by z naught plus zl times tanh of j beta x. One thing to notice here is, remember that we set alpha equal to 0 for a lossless line. However, if alpha was not equal to 0, then this j beta here would just be equal to gamma. I mean, we would have to substitute the j beta for gamma. So the actual complete formula is Zin equals z naught times zl plus z naught times tanh of gamma x divided by z naught plus zl tanh of gamma x, where gamma again is equal to alpha plus j times beta. So this is the actual formula. And now so this is the final formula. So if you know alpha, you know beta, then you can you know the characteristic impedance z naught and the load impedance zl, and you want to calculate the input impedance at any point x. You just substitute all the values here and you get the input impedance. Now let's see what happens when x is equal to 0. So at x equals to 0, Zin is equal to z naught times zl plus, so the tanh of 0 is equal to 0 If you look here on the graph, these are the graphs of the hyperbolic functions. Let's wait for them to open. Why is it taking so long? Hold on. Okay, so no internet. I don't know what happened to my internet. Hold on. Okay, so it doesn't matter. So the tanh of 0 is 0. So this term here disappears. This term on the bottom disappears. So it's ZL plus 0 divided by Z naught plus 0. So you can see here, this Z naught cancels with this Z naughts, and this is equal to ZL. So as you can see, also this formula makes sense, because when x equals 0, we are right at the load. If you look here, we are right at the load. So the input impedance at the load is just the load. So the formula is correct. Now let's just work a little bit more with this formula here for a lossless line, which is usually the case. For a lossless line, there's another fact, which is the tanh of a purely imaginary number. Let's say tanh of jx is equal to j times the tangent function of x. So this is the hyperbolic tangent, and this is the normal circular tangent, trigonometric tangent. So we can also write this here as z in is equal to z naught times zl plus z naught times j times tangent of beta x divided by z naught plus zl times j times the tangent of beta x. So this is usually the formula that we use, because usually the characteristic impedance is just a real number, which means that the line is lossless. So here we go. So here is the formula for the input impedance at any point on the line. And as you can see, it's a complex number, of course, because the impedance is a complex number. And so let's see, there are a couple of cases that we can deal with here, because tangent, if you remember, the tangent function is the tangent of this angle here, theta. When the angle is pi over 2, tangent is infinite. When the angle is equal to 0, then the tangent is 0. So beta x is the angle on here. And another thing that I didn't mention before is how do you calculate beta? Beta is equal to 2 pi over the wavelength of the signal. Remember, we're dealing with AC signals, and AC signals, they are sine waves like this. This is x. And we can define the wavelength. Of course, the wavelength is defined, which is the points from here to here. And this is the wavelength of the signal. Remember that the signals on the transmission line are traveling close to the speed of light. So they travel with the propagation velocity Vp for propagation. If you remember the relationship for electromagnetic waves, we have that the frequency times the wavelength is equal to the speed of light. So in this case, we don't have the speed of light, because in the transmission line the signals travel more slowly than light. So frequency times the wavelength is equal to the propagation velocity. And so the wavelength is equal to the propagation velocity divided by the frequency. The frequency is the frequency of your AC signal. So to calculate beta, we just write 2 pi divided by the wavelength, which is this. So this is the propagation velocity. And here is the frequency. This can also be written as omega divided by the propagation velocity. So this is what beta is, omega divided by the propagation velocity. So if you know your omega, if you know your propagation velocity, which is given by the dielectric, which is equal to the, if you remember, the speed of light is equal to the square root of, it's 1 over the square root of epsilon naught times mu naught. and this is the dielectric constant of empty space. So this is the permittivity of free space, and this is the magnetic constants, the permeability of free space. However, we are not in free space in a transmission line, so the actual speed will be changed. So the V propagation will be equal to 1 over the square root of epsilon relative of the dielectric, which is the dielectric constant, times epsilon naught times mu naught. Mu naught does not change in this case because well, we assume that in most transmission lines the material is not magnetic, so the magnetic constant is not changed. So the propagation velocity will be equal to 1 over the square root of this epsilon relative times epsilon naught, can be written just as epsilon, which is the epsilon of the transmission line, times mu naught. Let me just increase the size of this page here. Let's paint it black. Now choose a brush. Okay, so the propagation velocity is equal to 1 over the square root of epsilon times mu naught, which is equal to, now propagation velocity, remember that it's 1 over the square root of epsilon relative times the square root of epsilon naught mu naught, which is just equal to 1 over the square root of epsilon relative times the speed of light. Remember, the speed of light is just this. So we can write the propagation velocity is equal to simply the speed of light divided by the square root of the relative dielectric constant of your material. So with this information, we can find the constant beta here. And so once you know the constant beta, you can calculate beta x, because x is just a position on the line. So this will be equal to omega times x divided by Vp. And once you find that, you can calculate the input impedance Zin. Okay, so we have done a lot about transmission lines, and this takes some time to absorb. This is a very interesting subject. It's a very complex subject. It involves a lot of electromagnetics. And in the next video, if you see here, it's quite cumbersome to calculate the input impedance, the reflection coefficients, because they involve imaginary numbers, and it's just disturbing. It's a lot of work to calculate with imaginary numbers if you don't have a calculator, for example. There is a chart. There's a tool that we use called the Smith chart, which is a tool, which is a graph that helps us to calculate both reflection coefficients, input impedance at any point on the line, reflection coefficients at any point on the line, and it helps us do lots of other things. And we're going to talk about it on the next tutorial. Just for now, the Smith chart, just to give you a primer of what it looks like, the Smith chart is a circle like this. There's a line here, there's a line here. Basically, this is the complex plane, and there are some lines that go like this here, like this, other lines that go like this, and there are circles that go like that, circles inside circles, another circle here, another circle here, etc. And this Smith chart helps us to calculate all of these parameters very easily, and we're going to talk about this on the next tutorial. So I hope you have been enjoying the tutorials, and I'll see you in the next tutorial. Thank you.